In this section, we want to talk about constructing estimates for one sample averages, meaning we have one sample set of data, and we're going to estimate either the population mean or the population median, which we'll generally refer to as averages. So the sample mean which gets notated as x bar, so x with a bar drawn over the top of it, is considered to be an unbiased estimator for the population mean. And again, we'll indicate the population mean with this Greek letter mu, which is a U with a long tail off one side. So we either have a population mean mu, or a sample mean x bar. So our sample mean is an unbiased estimator for the population mean. That means if we took multiple samples of the same size, then the mean of all of our sample means would be the same as the population mean. So if we had the time and resources, we could go out, collect sample data, evaluate a sample mean, go out, collect new data with a different sample, get a sample mean, repeat that process over and over again, and then average all of our sample means to get the population mean. So in reality, we can't do that. We can't take sample after sample. So we have to rely on a single point estimate or a single sample mean to be the estimate for a population mean. So to estimate mu, the population mean, we're going to start with a point estimate. Which in this case is going to be our sample mean, x bar. And then we're going to stretch that value into a range of values using a margin of error. So we know that each sample mean is a little bit higher, a little bit lower than the actual population mean. So if we take x bar plus or minus some margin of error, or we can represent that as some lower bound, comma, some upper bound as an interval, then we can assign a confidence level to state how confident we are that that interval contains the true population mean. When we estimate means, there are two cases to consider. The first one is where the population standard deviation which we represent with the Greek letter sigma, which is an O with kind of a straight line coming right off the top of it. So that's sigma. So the first case is when our population standard deviation is known. The second case is when our population standard deviation, sigma, is unknown. So case one, if we know the population standard deviation, that's basically a case that doesn't really come into play in real world scenarios. If you looked at the formulas, you could get into this a little bit deeper and understand why, but essentially the idea is if we know the population standard deviation, to calculate that we already had to know the population mean. So in reality, we probably never encounter a case like this. So we'll throw that first case out and really just focus on case two. So whenever our population standard deviation is unknown, then we have to use the sample standard deviation, which we represent with a lowercase s, to construct our estimates. So essentially when we're estimating a mean, a standard deviation has to be used as part of those calculations. This will be happening in the background with StatCrunch. If we know the population standard deviation, we can use that. In cases where it's unknown, which would be the cases we'll consider in this class, then we have to rely on the sample standard deviation. So we run into a little bit of a problem that S is not, sorry, there should be a not in there. S is not an unbiased estimator for the population standard deviation. So S is a biased estimator for sigma, meaning we increase our possible error whenever we use it to construct estimates. So what we're going to have to do is something else, which again is mostly being taken care of in the background with StatCrunch, but we're going to have to do something different to help compensate for that error. In case one, whenever the population standard deviation is known, our estimates are being constructed and calculated using a normal distribution. In case two, when we're basing our results off the sample standard deviation, we're introducing that additional error, we're going to use something called the t-distribution. So since S is an unbiased, or is not an unbiased estimator, it's a biased estimator, we need to make our final confidence interval wider using the t-distribution. So the t-distribution is another continuous symmetric and unimodal distribution, but it's generally shorter and wider than the normal distribution. So for instance, if we looked at values that were one standard deviation away using the normal distribution, we would end up with intervals from here to here. So this would be at -1 if our mean is 0, and this would be 1 standard deviation away. Since the t-distribution in green here is a little bit lower and wider, that means our values that are 1 standard deviation away will be a little bit farther away. So essentially the result is when we use the t-distribution to construct these intervals, we end up with an interval that's wider than it would normally be if we were using the normal distribution. And again, the reason we're doing that is because we're using the sample standard deviation as part of that calculation, which is a biased estimator. So it's adding additional error to our problem. So that's really all happening in the background of StatCrunch, but just to introduce some of that information, a little bit of the theory behind what we're doing here.